All right, welcome back to A Hitchhiker's Guide to the Solar System. This is going to be lesson 2 of our investigation into the solar family. So why don't you climb aboard this unicorn with me and we will shuttle off into outer space. Today's lesson is going to be called The Wanderers. It is part 1 of 2 lessons, which are going to be about the planets. And we will get to the lesson title in just a moment. Because, like many of our scientific terms, the Wanderers is a term that goes back to ancient Greece. And in ancient Greek times, there were many constellations that people had been creating stories around. They looked up at the skies and they told stories about the stars that were out there. The background picture here is of one of those stories. And it turned out that once people really started paying attention to these stars, most of them stayed relative in a relative position next to each other. So they might, whole constellations might move across the sky as months progress, but there were a few stars that would actually move faster relative to the background stars. And the Greeks ended up calling these things the wanderers, which or in their language, was planets. And now we know that planets are these massive bodies inside our own solar system that are held in orbit by the gravity of the sun. So the wanderers is a translation of planets, which is Greek for the wandering stars that they saw in the sky. Today we are going to be continuing with our essential question of what are the basic components of the solar system. We talked about the sun at the center of it all yesterday in lesson 1. Today we're going to be talking about the terrestrial planets, Mercury, Venus, Earth, and Mars. We're going to be adding to our Hitchhiker's Guide, so make sure you have that with you. Here's mine that I have sort of started. Make sure you got that with you. We are going to be working on that today as we go. So pages 2 and 3 will be all about our terrestrial planets. As mentioned previously, planets is a term that the ancient Greeks used. As they studied the stars, they knew their positions and orientations quite well. They even gave names to groups of stars, which we now call constellations. Among the constellations, however, were a few small twinkling objects that moved. They didn't stay fixed, and they didn't stay fixed relative to the background stars. They were named the wanderers, or planets in Greek. So what are planets and how did they get here? These are the questions we're going to hope to be answering throughout these next 2 lessons. To understand the life of a planet, we need to go back to the life of a star. When protostars are forming, the planets are also forming. If we consider the life of a star, remember it goes from nebula to protostar to main sequence star, red giant, planetary nebula, white dwarf. And right now, our sun is a main sequence star that looks just like this right here because this is an image from NASA. Now, a long time ago, about 4.5 billion years ago, our star did not look like this. In fact, it looked more like this. This is a protostar, and this is what our planet was born out of. If you recall, at the very center of this swirling flat disk here is the protostar, where a lot of the mass from the cloud is starting to condense, the gravity is getting stronger there, and eventually nuclear fusion occurs. However, this big disk that's swirling about is still filled up with all sorts of pieces of dust and gases and different things. And it turns out that this is where all of our planets are born. So we call this the accretion disk, the protoplanetary disk, and you can kind of think of it as, well, let me show you. I'm going to use this website here. I have it linked in the slides if you want to go look at this yourself, but it has some nice little demonstrations of how planets form. Let's see. Okay, so first, just to get an idea here, we are going to watch this movie of a nebula as it collapses and contracts and turns into stars. So we're going to see an animation of how stars actually start to form. Again, we start with a cloud. There's tiny differences in it, and those tiny differences lead to slight differences in gravity. The gravity starts acting stronger in different locations, and that gets this big, almost homogeneous cloud to start changing. And now we can see there's differences in it. It's more dense in this region right here than in these outer regions over here. As we click through, we are going to zoom in a specific part of this cloud that would be like the star nurseries that we talked about. So this is a nebula, and then we're going to zoom in and look at a stellar nursery. Okay, so this point right here is the most dense part of the cloud, and you can see it's starting to swirl, creating that accretion disk. And in this case, it's so dense that it's actually making multiple stars. Those little spheres that come flying out of there are different stars that are being born. And if you look up here, this is happening over the course of hundreds of thousands of years, and it's a simulation, but it gives you the idea of what star birth actually looks like. So it's kind of chaotic, a lot of swirling. These really massive bodies have the pull of gravity is acting between them, and it causes this circular orbit of each other. All those little light circles getting thrown about are new stars being born again. And then the sphere around them is going to be the accretion disk. Like right here, we can see. Okay, so I'm just going to stop there and come down to this next page because it also has a cool little. Okay, so hopefully you can see this. I'm just going to restart it. We've got our accretion disk here, and it starts with a bunch of little circles. And what happens is when they run into each other, they actually glob onto each other and combine, and that leads to bigger and bigger globs until we're just left with these four. We have, believe it or not, 4 terrestrial planets, so that's what these represent. I'm going to start it over just so we can watch that one more time. A bunch of little tiny globs, we would call those planetesimals, and then when they get close to each other, they actually combine. As gravity pulls them into each other, they combine into bigger and bigger planetesimals until we're at these last 4 that became our planets. In this case, we would have Mercury, Venus, Earth, and Mars. Okay, so hopefully that gives you a little bit of an idea of how the planets were born. Okay, there are 2 types of planets. I said this is going to be a 2-part lesson on planets, and we have terrestrial planets and we have gas giants. Let's look at those terms quick. Terrestrial, I want you to think terrain, all right? Terrain would be like the earth or the soil that you move over. You could have sandy terrain, muddy terrain, rocky terrain. All of that is like earth, it's a solid. A terrarium, that's where Trouble the Gecko lives, okay? Terrarium has it's like a cage where you keep a land creature as opposed to an aquarium, aqua, made out of water. Terra is made out of earth. So terrarium is an earth cage like we have in the back of the classroom, and terrain is the type of earth or material that's on the ground. So when you hear terrestrial, think terrain, terrarium, think solid, and planet Earth is a prime example of a terrestrial planet. It is a solid, rocky planet. The other type of planet is called a gas giant. And with gas giants, I want you to think big, all right? These things are quite voluminous. They look kind of cloudy on their surface. They are gaseous, thus the gas part of gas giants. Most of them have rings, and the planet that most exemplifies this might be Saturn or Jupiter. Okay, so those are the two classifications of planets that we have: terrestrial and gas giants. And today we're going to be focusing on the terrestrial planets. And here they are. This image, courtesy of Wikipedia again, shows the 4 terrestrial planets in our solar system. So these are the earthy, rocky planets in our solar system. It starts with Mercury, which is closest to the sun, then Venus, Earth, and Mars. A lot of work is being done right now trying to get humans to Mars. You've probably heard about that. We'll probably talk about some of those missions in a bit, but for right now, I just want you to know that there are 4 terrestrial planets: Mercury, Venus, Earth, and Mars, and they are ordered in this way. So if the sun is on this side, then Mercury is the closest, then Venus, Earth is the 3rd planet from the sun, and then Mars. So that's what they look like on the outside. Let's take a look at the inside of these. What makes a terrestrial planet terrestrial? It turns out that all terrestrial planets have a solid crust on the outside. Solid crust on the outside. We think of these as the tectonic plates that are moving, and our continents are made out of them. Earth has a solid crust. Venus, Mercury, Mars, they all have a crust. So they're solid on the outside. Then underneath they have something called the mantle, which is more rocky substance. It is a solid, but it actually moves sort of like a fluid over billions of years. So it has a mantle. And then at the very center, it has something called a core. And all terrestrial planets have those 3 components: the crust on the outside, the mantle, which is this rocky material in the middle, and then a metallic core, which is very hot and very dense. All planets are made out of rocks, mainly, something called silicates. So Earth is mainly made out of silica. Last but not least, all terrestrial planets on the surface are going to have things like craters from impacts. They're going to have valleys and canyons and atmospheres. That's what makes something a terrestrial planet. Made out of rock, has a solid crust on the outside, and it's got craters, valleys, canyons, and atmosphere. All right. So as mentioned, all of these terrestrial planets are the closest. They're the 4 closest planets to the sun. So why is that? Why are the closest planets to the sun made out of solid things, and the planets that are further out, gas? Well, it turns out that when the sun was forming, it was very hot, as it is now. And it was so hot that the things very close to it, such as the metals and the rocks, could actually condense. It was hot enough for them to condense. However, once you got further and further away from the sun, it got cooler and cooler. And at a certain point, some of the things that were gases in here, things like water, things like ammonia, things like methane, they're all gases here. But once they get further away from the sun, they will actually condense and turn into solids. And what that means is that the planetesimals that form in here, when this big disk is swirling around, those solid pieces are actually just going to be the rock and the metal. But once you get past the frost line, it's going to be the rock, the metal, but then it's also going to be frozen water. It's going to be frozen ammonia, frozen methane. And since there's so much of that, it's going to lead to these larger gassy planets that are beyond the frost line. So again, closer to the sun as it was forming, the metals and the rock were able to condense because it was so hot close to the sun. And that's what formed the rocky metallic planetesimals. And then they would run into each other and get bigger, forming the terrestrial planets. Outside of the frost line then, hydrogen compounds like methane, ammonia, and water were able to freeze and accrete into these planetesimals. Since the abundance of those compounds was so much greater than the metals and the rock in the dust cloud, the planetesimals in the area outside the frost line were much bigger because there was more material flying around out there. More solids were flying around and running into each other, and that led to larger planetesimals, which then had more gravity, and it eventually had enough gravity to start pulling in some of the surrounding gases. And so at the very center of these gas giants, it's actually liquid, and they probably also have metallic cores, but they also are surrounded by the gases. So that's how gas giants were born. And again, I have a link to this down at the bottom if you're interested in learning more about that. But I just thought if you're curious, that's why the terrestrial planets are closer and the gas planets are further away. Okay. Now again, we're talking about the essential question, what are the basic components of the solar system? We've already talked about the sun in the previous lesson. Today we talked about terrestrial planets, Mercury, Venus, Earth, and Mars. I gave you a brief outline of what they were, how they formed, where they are relative to the sun, but not a lot of information. What you're going to do is on pages 2 and 3 of your Hitchhiker's Guide, you are going to give me some information about those 4 planets that I did not yet share with you. You could also include, like you did with the sun, the diameter, the surface temperature, and the mass of each of those planets. Now, if you want to, you could add in some other interesting facts. Again, it's a Hitchhiker's Guide, so you might want to give some advice to a traveler coming to our solar system as to what to expect on that planet. Is it going to be really cold? Are they going to be able to breathe? Is there oxygen? Questions like that. So as you work today, in the link below in the description of this video, I will put a source for you to use to find some of this information. I also put a link to the slides that I used in today's lecture. So the goal today is to have pages 2 and 3. This first page should be with the sun. I don't have anything on it because, well, it's not mine to do. But then 2 and 3 should be about Mercury, Venus, Earth, and Mars. You can choose how you want to do it. If you want to do 2 on each page, maybe you'll do a brief intro on page 2 and then more interesting facts on page 3. I don't really care as long as pages 2 and 3 cover those 4 planets in some way. That's your goal for the rest of the class today. So go ahead, get to work. The links are below in the description. Thanks and have a good day.